Hi everyone, and welcome to the first of two videos going through some past exam questions on electrochemical cells and fuel cells. So the first question we've got here has given us three different redox systems, and it says two cells were set up in an experiment to compare the standard electrode potentials of C, D and E. The signs on each electrode are shown. So we can see here that we've got silver with ammonia and this silver ammonia ion here. So this is, I'm just going to write these in here so it's clear what's going on. So this is redox system C, and then this one with the Cn minus ions is E, and then here we've got C again on this side, and this one is D. So it then says list the three redox systems in order by adding the labels to the table below. Okay, so the most negative one, so E is more negative than C, and then here C is more negative than D. So E must be the most negative, then C, and then D. Okay, so that's quite a nice easy question. You don't need to think about what's going on here. If it's the negative electrode, it's the more negative value. So it is actually as straightforward as that. And that's just only giving us 1 mark for that. So that's a nice easy one to start off with. Okay. It then says a standard cell is set up between redox system D and a standard hydrogen half cell. The standard cell potential of redox system D is plus 0.34. The cell delivers a current for a length of time. The pH of the solution in the standard hydrogen half cell decreases. Okay, so the first thing it's saying is, what is the pH of the solution in a standard hydrogen half cell? Okay, well, we know that in the standard electrode, then the concentration of the H plus ions must be 1 mole per decimeter cubed. Okay, because that's the standard concentration, isn't it? Okay, so if we want to then work out the pH, this is actually using a little bit of stuff from acids, that the pH is a negative log of the H plus concentration. So the pH is a negative log of 1. Okay, so if we do minus the log of 1, we get 0. Okay, so it should be pH 0. Okay. Then it says, explain in terms of electrode potentials and equilibrium why the pH of the solution in the hydrogen half cell decreases as this cell delivers current. Okay, well, if the standard cell potential is plus 0.34, then it must mean that the electrode potential of redox system D of that half cell must be 0.34, because we know that the electrode potential of the standard hydrogen half cell would be 0. Okay, so what we can say then is that the electrode potential for redox system D is more positive, I can't spell, than the electrode potential for the standard hydrogen half cell, which would be 0. So that means then that the standard hydrogen half cell would be oxidized and the redox system D would be reduced. Okay, so therefore the reaction that must be going on in the standard hydrogen half cell, and it's a bit tricky because they haven't actually given us this anywhere. They haven't given us the equation, so we need to actually remember that we need to know what the equation is for the standard hydrogen half cell. Okay, so this means that the equilibrium, if it's being reduced, we can say the equilibrium is shifting to the left. Okay, so the equilibrium in the standard hydrogen half cell shifts to the left. And we could write out the equilibrium here, but I think it's probably better if we just write out the actual equation. I can say it's shifting to the left here, right, because the redox equilibria are always written as reduction going from left to right. Okay, and we know that because it's the least positive one, redox system D is more positive, So the standard hydrogen half cell, if it's less positive, is going to be oxidized. So it would go from right to left. So therefore, the reaction that would be happening would be that instead of it being reduced, so gaining electrons, it must be being oxidized and losing electrons. So the reaction must be that H2 gas is turning into 2H plus ions and 2 electrons. Okay. So we've talked about electropotentials, we've talked about equilibrium. Now we just need to link this back to the pH. Okay. So what would happen is that if this reaction is happening more, then we would increase the amount of H plus ions. Okay, and so if we increase the concentration of H plus ions, the pH then would decrease. Okay, remember the higher concentration of H plus ions leads to a lower pH. Okay, so we can just then say this increases the concentration of H plus ions, so the pH decreases. Okay, and then it says write the equation for the overall cell reaction that takes place in this cell. Okay, well, we know what's happening with one of the half equations because we've just written that out. Okay, so let's just write this underneath again. So we know that this reaction is happening this way, and then the other one is redox system D. So if we look up that, where's redox system D? This is this silver one, and we said that redox system D was the more positive one, so redox system D would be being reduced. So this equilibrium would be going from left to right. So it would be Ag plus electrons going to silver. So this would be our other half equation. And so the overall cell reaction would be the combination of those two. So we just have to times this one by 2, right? So that the electrons would cancel out, and then we can add them together. So it'd be 2Ag plus H2 goes to 2H plus and 2Ag. Okay. Right, moving on. We then get a question here where they've given us a load of electropotentials again. So a lot of these questions do look kind of similar. So what's it saying here? We've got some electropotentials. Complete the electron configurations for Fe2 plus and for Br minus. Okay, now for this, we're going to need to have a look on the periodic table. So if we find iron on our periodic table, then iron is going to end up with its electron configuration. It's going to end up as 4s2, 3d, 1, 2, 3, 4, 5, 6. Okay, but then if it's an Fe2 plus ion, it would have lost 2 electrons, and it would have lost the 2 4s electrons, won't it? Remember, 4s fills up first, but it also empties out first. So Fe2 plus, we carry on from here. Notice they do this so that you can't do the noble gas as a shortcut for writing the electron configuration. You have to carry on from here. So you're going to have to write this out properly. 3p6, and so that would get us up to argon. Then it would be 4s2, 3d6, but then it would have lost the 2 4s electrons. So it would just be then 3d6. Okay. And then Br minus is going to go all the way up to 4p5, but then it will have gained an electron, so it'll be 4p6 at the end. Okay. So this is going to be a bit of a long one. 3p6, 4s2, 3d10, and then 4p6 at the end. Okay, because it's gained 1 electron. Okay. Right, it then says, predict the products of reacting iron separately with iodine, bromine and chlorine. Explain your predictions using the electropotential data above. Okay, so what we can say then is, let's look at the electropotentials compared to each of these. Okay, so if we look at for the one that involves iron as a solid, its electropotential is more negative than, well, actually for all of these, right? So in every case, this would be oxidized and the halogen would be reduced. Okay, so that seems a bit, right, it's the same for all of them. That seems a bit too good to be true. And also, why have they put this electropotential in there then, if all they're asking us about is the iron? What we also need to look at is what's going on with this one. Okay, because if the iron is being oxidized to Fe2 plus, will it also be oxidized from Fe2 plus to Fe3 plus? Okay, and we can see that comparing this to the iodine, then this electropotential is more positive than the iodine. So this one would be reduced. So for the iodine, we wouldn't also get the Fe2 plus being oxidized to Fe3 plus. Okay, but we would get that happening with both the bromine and the chlorine. Okay, so when iron reacts with the iodine, the products will be Fe2 plus and I minus, as the electrode potential for iodine is more positive than the electrode potential for Fe2 plus, but less positive than the electrode potential for the Fe3 plus. Okay, so it will reduce, it will oxidize the iron to Fe2 plus, but it won't oxidize the Fe2 plus to the Fe3 plus. Okay, and that's all we need to write, I think. We'll just look at the mark scheme in the background here. Yeah, we don't need to write anything else. We're just comparing them. Okay, but then we can say when the iron, it's only 3 marks this question, so by the time we've talked about all 3 equations and we've linked it to the electropotential values, I think that's all we need to put. We don't need to start writing equations or anything like that. When iron reacts with bromine, I'm going to write these two together rather than write them out separately, otherwise I'm going to be here all day. Reacts with bromine or with chlorine, the products will be Fe3 plus and Br minus or Cl minus, as the electrode potential for bromine or chlorine is more positive than both the electrode potential for iron 2 plus and for iron 3 plus. So it's going to oxidize the iron to the Fe2 plus, and it's going to then oxidize the Fe2 plus to the Fe3 plus. Okay. So just watch out for those. And sometimes this was kind of obvious because you think, well, why have they given us this other electrode potential? Are they really going to give us 3 marks for saying, well, in every case it's going to reduce the iron to Fe2 plus? How is that a 3-mark question? So watch out for that. But sometimes they're a little bit less obvious with these. There can sometimes be a whole string of different electrode potentials, and this might be part D of a question or something. But watch out for, if you've got 2 electrode potentials involving the same element, that they will sometimes want you to say, oh, it will do this, and it will then also do that as well. Okay, that is definitely something that's worth watching out for, because it's the kind of thing that they do like to put into the exam. Okay. Okay, and then finally, the last few questions we've got here then is talking a bit more about fuel cells. So it says here we've got direct ethanol fuel cells are being developed, okay, and you're not expected to know any details about these fuel cells, right? They will give you information. It specifically says on the specification that you need to know the general ideas, but any sort of details or things you've got to remember, they'll give you information on the paper. Okay. So it says this direct ethanol fuel cell half equation for the reaction at the ethanol electrode is shown here. State one important difference between a fuel cell and a modern storage cell. Okay, so this is the kind of thing that you are expected to know. And really all it's asking you for is kind of a definition of a fuel cell. Okay. So the key thing about a fuel cell is you have to keep providing it with the fuel, and that fuel reacts with oxygen. It's not just a redox reaction that's happening in solution. You have to provide it with the fuel. Okay, so we can say in a fuel cell, a fuel reacts with oxygen to generate a voltage, or to generate electrical energy, we could say. Okay. But it's this idea of the fuel reacting with oxygen. The overall reaction in a direct ethanol fuel cell is the same as for complete combustion of ethanol. Write the equation. So here you go. You're not expected to just know what the overall equation is, but from your other knowledge, you should know what the equation is for combustion of ethanol, and it's just that equation. Okay. So complete combustion of ethanol, this is ethanol here. It doesn't say state symbols or anything here, so don't have to worry about that. So it's just ethanol. It's reacting with oxygen, like we said. And if it's complete combustion, it's going to make carbon dioxide and water. And then we just need to balance it. So there's 2 carbons. We've got 6 hydrogens, so that's going to have to be 3. And then we've got 3 and 4, so that's 7 oxygens. So I need 7 oxygens here. I've got 1 there. So this needs to be 6 oxygens, so that's going to be a 3 to make that balance. Right, and then it says deduce the half equation for the reaction at the oxygen electrode. So here, this is the overall equation. This was one of the half equations. So what we can do is do the overall equation minus this half equation. Okay. So I'm going to write this out again. And this is a bit of a strange kind of method of doing this, but it does work. The 2 half equations would have been added together to give the overall equation, right? So we can do the overall equation minus that half equation. So if we take this one away, I'm just writing this out here. So if we take this away, the ethanol will take away the ethanol, leaves us nothing. We have the 3O2 and there's no O2 here, so we're going to be left with 3O2 minus 3H2O. Goes to the 2 CO2s, take each other away. 3H2O, take away 3H2O is nothing. And then we got minus 12H plus minus 12 electrons. So what we can then do is anything that's got a minus in front of it, just take it to the other side of the equation. Okay. So therefore we'd have 3O2 plus 12H plus 12 electrons goes to 6H2O. So add that over this side. And then just to tidy this up, just because we can, you should be able to see that we can actually divide this all by 3. And we probably should do that. I think it would give us marks. Yeah, we would get the marks for this because the multiplication doesn't matter. It's still the same equation. But it's usually a good habit to get into. If you can cancel something out to simplify it, then you probably should do. So if we divide all this by 3, we're going to get O2 plus 4H plus 4 electrons goes to 2H2O. Okay, and then finally it says using oxidation numbers, show that oxidation and reduction take place in a direct ethanol fuel cell. So if we then look at, let's go back to our overall equation, okay, and do the oxidation numbers from here. So we know that hydrogen's oxidation number is going to be +1. And we know that oxygen is going to be -2. So 5 lots of +1 is +6. -2 is +4. So the carbon must be in oxidation state -2 here. The oxygen here is going to be 0 because it's an element. And then here, the oxygen is going to be -2. Times 2 is -4. So the carbon must be +4. And here the hydrogen is going to be +1. And the oxygen is going to be -2. So what's been oxidized is the carbon has been oxidized from -2 to +4. Okay. From -2 to +4. And what's been reduced is the oxygen from 0 to -2. Okay, and that's it.